welcome back to a new session. Now, in this session, I have been requested to talk about applications of Bernoulli's equation. Now, before we do that, I want to discuss a few terms which I think you already know, but let us look at it in some more detail. So, we look at what we may call stagnation pressure. And the terms static pressure, dynamic pressure, and there is another term we will look at later, piezometric pressure. So let us begin by asking a question, and you can use your Akash tablet. We'll test it out again. We did it yesterday. So let me ask you a question. Can two streamlines intersect at a point? And this is a yes/no kind of a situation. So I'll give you two choices, yes and no. Please switch on your Akash tablets and give this answer, then we'll continue with the discussion. Achha, 1 minute. Please answer in 1 minute. All right, now most of you answered no, but the correct answer is A. So I'll explain. Of course, this will not occur at all points, but it can occur at certain points. So let me explain this. Let us take a two-D flow. So the velocity field V is say ui plus Vj. So if I show the coordinate axis x and y, let us say I have a curve and at a point of the curve I draw the tangent. Now if I say the angle which the tangent to the curve makes with the horizontal is theta, then you know that tan theta is dy dx. That is your basic calculus. Now suppose this curve could be any curve. Suppose this curve is a streamline. Then you know that the velocity vector is going to be along the tangent direction. So therefore, this, if I draw this triangle, this is the u component and this is the v component. So this will be v by u. Now suppose you have a point, let us look at a special case where u at a point is 0 and v at the point is also 0. Okay. So this is only of course for a streamline. Now what is dy dx for the streamline at the point P? So that you know is Vp by up. Now both numerator and denominator are 0. So this is indeterminate. It is of the form 0 by 0. Now you can use L'Hopital's rule to find the limit, and that can have two values. It can have more than one value. So the tangent is not defined if both the velocity components are 0 for a 2D flow. So such a point is called a stagnation point. Stagnation point. Now at a stagnation point, streamlines can therefore intersect because the velocities are 0. So I'll give you an example you may be familiar with. Let us look at potential flow, which we'll discuss later on in this, maybe tomorrow. Let us say you have a cylinder. This is the center of the cylinder, the x and y, and you have a, okay, I'll use another sheet. Let us say this is your cylinder. You have a coordinate system, Cartesian coordinates x, y. So this cylinder is very long in the z direction, and far upstream, let us say you have a uniform flow in the x direction. Let us say this is some u infinity. Now if I ask you to draw the streamlines, you know streamlines are everywhere tangent to the velocity vector. Then far upstream, the streamlines are going to be horizontal lines parallel to the x-axis. Why is it out of focus? All right. Now suppose I ask you another question. Let us say you have a streamline. Suppose I say this is a streamline. What is the volume flow rate across this streamline? The volume flow rate across the streamline is 0 because the velocity vector is tangent to it. The normal component of velocity is 0. Now you come back over here. This circular surface is the surface of a solid cylinder, and we'll assume that it's not porous, it is impermeable, so no fluid is going to seep through. So therefore you can say that this is a streamline, a circle. Now in many situations the flow pattern is symmetric, and you may have a upstream flow, the streamlines are all parallel like this. So you will have a central streamline which will come here, and this will go up, this will go down like this. So you can do a flow visualization and look at the streamlines, you will see streamline patterns like this. So I am showing the arrows just to give you an indication of the direction of the flow. Now you see that if you look at this streamline, it is coming horizontally over here. So dy dx is 0. Now this circle is also a streamline, and at this point this horizontal streamline and this circular streamline, they are intersecting. Now that can happen only if the velocity is 0 here. Now let us, this concept of stagnation point is in the context of inviscid flow. Now in your preceding lectures we have talked about, my colleagues have talked about the no slip boundary condition, etc. Now simple minded way to think about it is a fluid sticks to a wall because of viscosity. So if you have a viscous fluid which satisfies the continuum hypothesis, and if you have a solid wall which is at rest, then the fluid particle at the wall will also be at rest. But if it is an inviscid fluid, then it can slip along the wall. So if you look at inviscid flow over the cylinder, you will see that the velocity of the fluid particle at these points may not be 0. We will actually solve it for irrotational incompressible flow tomorrow and find out what is the velocity on the surface. Okay. But anyway, what I am trying to say is that if you look at this circular streamline, which I am showing again in red, at different points on this circular streamline you will have a velocity, but at this point and also at this point, because the streamline will go like this, the velocity has to be 0 because there are two tangents. See, if you look at the tangent to the circle, it is a vertical line, and if you look at the tangent to this, it is horizontal. So here there are two tangents. So two streamlines are intersecting at a point. So this is what we will call a stagnation point, and the pressure at that stagnation point is what you call stagnation pressure. So in this example, we will call this the forward stagnation point, and the one here we will call the rear stagnation point. So if I say this is A and this is B, then A is the forward stagnation point and B is the reverse stagnation point. Now suppose I ask you to find the pressure at this point A. Now if you use Bernoulli's equation along a streamline, you can use it along this streamline. You will have, so let me draw another figure here. This is the streamline, let us say. Now I take a point here 1, and this point here is, say, what I call A. Now if you apply Bernoulli's equation in the standard, of course Bernoulli's equation in different forms. The one which was discussed just now by Professor Chakravarti is the simplest form. So here you are going to have E1 plus half, now we are taking rho to be constant, rho V1 squared, now plus rho G, he was using Z for the vertical coordinate, equal to V2 plus half rho V2 squared plus rho G Z2. Now suppose this is a horizontal cylinder like this, okay, then the Z for 1 and Z for A will be the same, and you can cancel them out. Otherwise also sometimes the difference may be negligible, so we will not worry about the change in the potential energy. Now of course here I wrote 2, so let me call this point 2 maybe. At this point 2, the two streamlines are intersecting, so therefore the velocity here has to be 0. So this P2 or PA, whatever I called it earlier, this is your stagnation pressure. Now what is V1? V1 is a point which is far upstream, and there you are given that the velocity field has a uniform flow approaching in the x direction. So your V1 is nothing but u infinity. The substitute infinity is given to give you the impression that it is at infinite distance from the cylinder, and P1 will be the pressure upstream, which you can call also P infinity. So you are going to have P infinity plus half rho u infinity squared is equal to P, and this you can call the stagnation pressure. I will call P stag. So for of course here we are assuming also that rho is constant. So for a constant density inviscid fluid, the stagnation pressure here is the sum of this and this kinetic energy. Now to distinguish this pressure, which we are writing as small p from this, some authors call it static pressure. And this half rho infinity squared, this is called dynamic pressure. So the sum of the static pressure and the dynamic pressure is what you call stagnation pressure. So static pressure is nothing but the pressure we were talking about earlier. To distinguish it, if you get confused between what is pressure and stagnation pressure, to emphasize this idea, some authors call it static pressure. And this, of course, it has a units of pressure. It is not really pressure, but it is called dynamic pressure. So if you now this Bernoulli's equation was derived from balance of momentum. It can also be derived under certain conditions from balance of energy. Okay, so it represents both the conservation of energy and conservation of momentum under some specific conditions. So you can think of it this way, that if you have a fluid particle here, it is moving along this streamline, and when it comes here, it has been brought to rest. So when the particle has been brought to rest, and this is an inviscid fluid, so this is a reversible process, the kinetic energy is converted into pressure over here. So this was there because of the motion of the fluid. So this is kinetic energy per unit volume. So that is why it is called dynamic pressure, because it has something to do with the motion of the fluid particle. Now this can be used for flow measurements. You can use this Bernoulli's equation in this form to measure fluid velocity using a pitot tube. So let us look at the principle of a pitot tube. Now suppose I have flow over a wall. So this is a solid wall, let us say, and this is of course an exaggerated view. Let us say we have a hole drilled in the wall, and you can have a U2 manometer here. Now let us say you have a fluid which is flowing this way. Now pitot tube is a tube which is kept opposite to this flow direction. So you have a tube here, which is aligned with the direction of the flow, and you can connect it this tube. So this fluid which is flowing could be air in this example, or it could be some other fluid also. So here this is I have drawn a figure for external flow, that is the domain of the flow is going to infinity. So this is a plate and there is a fluid which is around the plate is of infinite extent. You could have a similar thing in a duct. So you could have, let us say, if I draw two lines, this could be two parallel plates, and you can have a hole drilled in one of the walls, and you attach a tube here, and you put another tube and you can connect it to a U-tube manometer. So let us take two examples. This is air and this is say water. Now if you want to measure the pressure using a manometer, then you have to have a manometer fluid which is different from the fluid whose pressure you want to measure. So here it could be water, but here it cannot be water. So let us say here it is mercury. Now which pressure will be higher, this one or this one? Okay. So if I show the manometer levels, you may have something like this. Let us say this is your manometer fluid. And this manometer deflection, suppose I say is H with a subscript m. So this is H with a subscript m. So this deflection can be measured, and the density of this fluid, let us say, is rho m, m for manometer. So this is rho m. So here in this example, the manometer fluid could be water, alcohol, mercury, whatever it is. Here it cannot be water. So let us say here it is mercury. Now let us apply the Bernoulli's equation between a point here and a point here. Now the fluid in this manometer limb, this is at rest. The fluid is flowing over the plate over here. Now if you have a tube which is aligned with the direction of the flow and in the opposite direction, then this column of this layer of fluid here, this will also be at rest. So essentially this will be a stagnation point. Okay. Now of course this is just a schematic. If you look at it this way, here this is the tube, fluid is coming this way, and the streamlines will go like this because the presence of the tube will disturb the flow, and you will have a central streamline here, similar to the figure which I drew earlier for the case of the cylinder. So here you will have a stagnation point. So if I say this is 1 and this is 2, you are going to have P1 plus half rho P1 squared is equal to P2. I am not writing the other term because the velocity here is 0. Now we have to look at how we can, so from here the velocity then V1 squared, half rho V1 squared is P2 minus P1. So the difference of pressure between these 2 points will give you the kinetic energy. So from here V1 is twice P2 minus P1 upon rho square root of that. Now this rho of course is the density of the fluid. Now of course if it is air also, we are assuming that the Mach numbers are small, so the air can be treated like an incompressible flow, although it is a compressible fluid with a constant density, otherwise you cannot apply the Bernoulli's equation. So in the main workshop, perhaps if you have time, we can discuss what happens if consider the compressible defects for a gas. And here this rho in this example will be rho of the water. Now let us see you want to measure the pressure using the principle of a manometer. So consider this column of liquid over here which is at rest. So if you have a continuous mass of fluid which is at rest, then from your hydrostatics you know that the pressure is the same at the same horizontal level. So if I take this level here and I have a point here which I call say small a, and I have a point here which I call small b, then you know that PA will be equal to PB. Now of course if I take a point here say C and I take a point here D, PC will not be equal to PD, although it is at the same horizontal level, because the fluid here is air and the fluid here is, this is the interface between the air and the mercury. So anyway, let us look at this. What is PB and what is PA? Now you want to link PA and PB to P1 and P2. Now here for the timing, I will give the justification later. We will assume that because the flow is in this direction, in the perpendicular direction the pressure varies linearly, just as it for hydrostatics. So this P1, PA I can write as P1 plus the effect of this weight of this column of fluid plus this column of fluid. So PA I can write as P1 plus rho g. Suppose I say this height is say h. So PC at this point will be actually P1 plus rho gh, and PA will be PC plus rho mg hm. So this pressure is the pressure here plus the effect of this. You have to consider the effect of this volume. So PA is P1 plus rho g h plus rho m g hm. Now similarly, if you look at PB, the pressure here, it is going to be P1, P2 plus, see this is this column, this layer of fluid is at rest. So P2 here will be the same as if I call this P3, okay, and the pressure at PB will be P3 plus rho g hm. So it is P3 is the same as P2. So this is plus rho g h plus hm. This total distance is this h plus the manometer deflection. Now these two will be equal. So you have P2 plus rho g h plus hm equal to P1 plus rho g h plus rho m g hm. Now you see that this term on the right hand side, rho g h, will cancel with this rho g h. Now what you want is P2 minus P1. So I can bring this term to the left hand side. So you have P2 minus P1 equal to, now I will move this term to the other side and you see that GHM is common. So we are going to get the difference of the densities, rho m minus rho g into hm. Now this, if I substitute over here, will be V1 will be under root of twice rho m minus rho g hm by rho. Now rho divided by rho is 1, and this I can write as rho m by rho. So therefore the velocity which you wanted to measure is given by under root twice rho m by rho minus 1 into g into hm. I can see this has this one is non-dimensional. G has units of meter per second squared, and this, of course, you can measure in centimeters, but you can convert it into meter, let us say. So you have meter square per second square under root, so it has the units of velocity. Now coming back to the previous example here, let us say the rho of the air is order of 1 kg per meter cube, or maybe 1.2, whatever it is. It would of course depend on the conditions, but this is what typically you will have in the lab. Now suppose this is water, then rho will be 1000. Rho m will be 1000 kg per meter cube. Suppose I say this is water. Then you look at this ratio, rho m by rho, this will be 1000 kg per meter cubed by something which is order of 1, maybe 1.2 kg per meter cube. So this is a large number, and if you are subtracting 1 from it, that will not, you can neglect this 1 in comparison with something order of 1000. So for the air water combination, you can say V is approximately root of twice rho m g hm by rho. Okay. Of course, if you want to use this, but many authors would use this. Now let us come back to this other example. So here the fluid density itself is 1000. Of course, it could be 990 or whatever it is. I am taking 1000 as a round figure. Now suppose this is mercury. I know the specific gravity or relative density of mercury is 13.6. So here your rho m will be 13.6 into 10 to the power 3 kg per meter cube. So we come back over here. For this case, rho m by rho is 13.6. Now if I say that I am going to use this expression, the error is going to be significant, because now 1 is not insignificant compared to 13.6. So for this case, for water mercury combination, if you look at this expression twice rho m by rho minus 1 g hm, this is going to be twice into 12.6 into g hm. Whereas if you take this expression twice rho m by rho gh, it is going to be twice 13.6 into ghm. Now the difference between 12.6 and 13.6 may give you 10% error. Okay. So do not use this approximation. This is an approximation. Okay. For such cases. So go back and look at the derivation here, and you see that right hand side involves the density difference of densities of the manometer fluid and the fluid whose pressure you want to measure at some point in that fluid. Okay. For the first case, this rho is negligible compared to rho m, so we can approximate it by rho m ghm. In the second case, when there are two liquids, you should not do it. When one is a gas, the other is a liquid, then you can do it. All right. Now, I'll answer the question why in this direction, although the fluid is flowing, I assume that I use the hydrostatic relation to find the pressure. Okay. So for that, you have to look at how pressure varies. Now tomorrow, Professor Chakravarti will talk about the Navier-Stokes equation. Yeah.
Hello. Hello, sir.
Yeah.
In case of manometer, once we are connecting with the pipe, so we should specify that the velocity pressure which is measured by at point 1, it should have zero velocity, means along
No,
the
point
axis.
1 is not zero velocity.
Yes, sir. So it should be the velocity of the fluid particle which are adhere with the wall. Not, I think it is with the center line. Since if we talk
No,
about
I am
the
not
water-
talking about center line here. This could be anywhere. You could have
means in the
something like this.
left limb.
Suppose this is a circular tube and you have the center line here. Okay. Now you could have your pitot tube, you can traverse the pitot tube across this section. So you can have the tube here, which is not in the center line. And what you have to do is make this is called a static pressure tap.
Yes, sir.
In the wall. And you need a different fluid here so that you have a manometer deflection. So you are getting the velocity at this point. Fluid velocity at this point.
Means the left tube which is measuring pressure, that should be the pressure of the fluid particle which are adhere with the wall. That is what I want to say.
Adhere with which wall? Wall
With
is
the
here.
Because once they are entering into the left limb of the U-tube manometer,
No, but
then
this is
they
not
don't
moving.
have any velocity.
This is not moving. This
There is no velocity component along the tube axis.
no, zero velocity does not mean that the pressure will
at
be.
the static condition means.
No, that is why I defined the stagnation pressure earlier.
Yeah.
This is not a stagnation point.
Okay.
Although the velocity is 0,
Mhm.
it is not a stagnation point. The concept of stagnation point is coming from inviscid flow.
Because I have read in some book, they are telling there is no this thing velocity along the tube axis while the fluid enters into the left limb.
No, no. See, the pressure at this point is stagnation pressure. The
Correct.
pressure at this point is not stagnation pressure.
Yes, sir. Correct.
Can you explain why? If you look at viscous flow, the velocity is 0 along the plate. But those are not stagnation points.
Hmm.
The concept of stagnation point is coming from inviscid flow. And if you have an inviscid flow, it will slip along this wall. But it will cannot, here it is obstructing the flow. It is in the opposite direction. Okay. The fluid which is in this horizontal tube and this vertical leg, this is at rest. This manometer fluid is at rest, and the fluid up to here is at rest, and here the fluid is flowing, but it is flowing in this direction. Okay. All right. Now, so what you can do is, of course, by inserting the tube, you are disturbing the flow, so there will be some error. You can't help it. Okay. So you want to make the tube as thin as possible. Okay. There are other ways of measuring. You can use a hot wire anemometer. You can use a laser Doppler velocimeter, but the cost of your instrument will go up. Okay. So this is a simple, inexpensive apparatus which you can set up in your laboratory, and what you can do is you can have a mechanism by means of which you can traverse the feeder tube across the section, and you can get the velocity at different points across the section. And then if you want to find the volume for it, you can integrate that velocity profile either using a numerical method or using a graphical method to find the volume for it.
Sir, can I have a question? Right side, sir. Sir, actually in one of the textbooks I have referred, to find the actual velocity, they are using the equation of root of 2 rho by rho GHM. And to find the actual velocity, they are using a coefficient along with this. V is equal to CV into root of 2GH.
No.
So is it correct? Because whatever velocity you measure from this equation
can
is...
you explain with reference to this? Please repeat your question.
Sir, in one of the textbooks I have referred, they have used the equation where V is equal to square root of 2 into rho by rho GH.
This one?
Along with that, yes sir, same equation. But along with that, they have stated to find the actual velocity, we have to measure it with a factor CV, which is less than 1. So is it correct?
No, of course. This, of course, is assuming that you can make the prediction using Bernoulli's equation.
No, so my doubt is whatever velocity you get from this equation is after the losses.
No, that will depend on where you are putting the... There are various aspects. Okay, let me discuss it. Suppose I have this setup, and now the fluid is flowing this way, let us say. What will happen? Of course, these levels may not be the same. Let me draw another figure. You have a pipe, and you have a hole drilled in the pipe. This is your center line, and you have a tube like this. But the fluid is now flowing this way. Will it work? It will not work.
It will not.
Because this will not give you the stagnation pressure. Okay?
Yes, sir.
So this tube is giving the stagnation pressure because the fluid is flowing this way and is obstructing it. Just as that is the reason why I first started with this example, simple example of this. This is like a bluff body, an obstacle placed in the flow which is coming this way. So this point is the stagnation point. Okay. Now similarly, here this point is a stagnation point, but here this will not sense the stagnation pressure. Now another thing is, suppose I have a tube this is the center line. Suppose the tube is bent like this. And the fluid is flowing this way. Will this sense the stagnation pressure? It will not. Okay. So what you have to do is, you have to align the stagnation, you can call it the stagnation tube. It has to be aligned with the direction of the flow. Alright. Now I will give you a justification why in this direction we are taking the pressure variation to be hydrostatic. Now tomorrow we will be covering the Navier-Stokes equations. So for the timing I am dealing with inviscid flow. So we will look at Euler's equations in streamline coordinates. Alright, so first I will start with Euler's equation of motion. You have rho times the acceleration, which you can say is a material derivative of the velocity, equal to the body force. You can use rho B as Professor Chakraborty was doing, or you might be more familiar with the case when the body force is just due to the gravity force, and minus grad P. Now, dV dt you can write as del V del T plus V dot grad acting on V. Now, let us say this is a streamline. We will take a coordinate system where you have a coordinate S, which is the arc length measured along the streamline from some reference point. So, let us say this is my reference point. This is if you take the distance along this line, the streamline up to this point, we will call it S. And you can have a unit vector which is tangent to this, which we will call E with a subscript S. Now, if I say capital V is the magnitude of the velocity, since this is a streamline, the velocity vector here is going to be tangent to the curve, and it will be a vector in the same direction, and the length of this vector, if this is 1, this will be V. So, you can say that V is the magnitude V into Es. So, this capital V is the magnitude of the velocity, and this is giving you the direction. Now, if you look at V dot grad, this operator, you can write it as V into Es dot grad. So, this you know from your vector calculus is the directional derivative along this direction S. If you look at grad, say grad F, in Cartesian coordinates you have del F del x I plus del F del y j plus del F del z k. Now, if I take I dot grad F, what will you get? I dot j is 0, so this term goes to 0, I dot k is 0, so this term goes to 0, and I dot I is 1, so you get del F del x. So, if you take the unit vector in the x direction, scalar product with the grad of f, you get the rate of change of f in the direction x. Similarly, if I take j dot grad f, you are getting del f del y. The rate of change is the directional derivative in the y direction, and k dot grad f is giving you similarly del f del z. So, here if you look at Es dot grad f, you are going to get del f del s. So, S is a coordinate which is along the streamline. So, we will take a coordinate with say a normal direction perpendicular to this vector Es. So, these two are unit vectors of unit magnitude, and this one we are taking a vector which is pointing towards the center of curvature. Now, let us come back to this expression for the acceleration. This is the convective acceleration. If you have steady flow, and we will be dealing with steady flow, then the first term anyway will be 0. So, if you look at V dot grad V, this you can write as the scalar V del of the vector V del s. Now, the vector V is V Es. So, you are going to get two terms from here, V into V del of Es del s, the other one is del V del s Es. So, this gives you V squared del of Es del s plus V del V del s Es. So if we go back and look at the acceleration term, say dv dt, it has the temporal part which is del v del t, and now you are going to have v del s es and v squared del of es del s. So the convective part now I am writing as two terms. One is the component of the convective acceleration in the direction tangent to the streamline, and this is another vector here. So we have to find what is this vector. Now es is a unit vector, so es dot es is going to be equal to 1, and this holds at all points along the streamline. So I can differentiate both sides with respect to s. So if you look at del del s of es dot es, this will be del del s of 1, which is equal to 0. Now this I can write as twice es dot del of es del s equal to 0, because if you have a dot b, the derivative will be a dot the derivative of b plus derivative of a dot b. These two are equal, so you get twice of this. So that means that if this vector del es del s is not 0, it is going to be orthogonal to es. So if we come back, of course this derivative could also be 0. So let us look at two cases. Case 1, say the streamlines are straight lines, let us say. Okay. Now in this case, the unit vector del es del s will be 0. Why? Because here the tangent vector is this way, it is a straight line. So these are your es, they are parallel vectors. Both have magnitude 1, and because it is a straight line, the direction is the same. So here the es is not varying with s. So in that case, if you come back and look at this term here, this term will be 0, it will not be there. Okay. Now let us look at a case 2. I will take simple case. Suppose you have a streamline which is an arc of a circle. Now if you look at the es at this point, it is in this direction. If you look at the es at this point, the magnitude of these two vectors are the same, they are both 1, but they are pointing in different directions. So the es vector is changing with distance along the curve. So here your del of es del s is not equal to 0. So let us try and find what it is. So if I take, suppose I say this is the center of curvature, I can draw a line over here and another line over here. If I say this angle is say theta, if I draw the horizontal line here and the vertical line here, this angle is going to be theta because it's an alternate angle. This one is going to be 90 minus theta, so this one is theta. Now if I take a coordinate system, say x this way and y this way, and this is es, then you know that es, it will have a component in the both x and y direction. The magnitude is 1, so the x component is cos theta I, and the y component is sin theta j. So this is changing along this, as you move along this streamline. So what is a des or del es del theta? This will be minus sin theta I plus cos theta j. Now let us look at this unit vector which is perpendicular to es. We are calling it en, the normal direction, which is pointing towards the center of curvature. This also is a unit vector, it has magnitude 1. Now it has a negative x component and a positive y component. So you see that en is minus sin theta I plus cos theta j, which is exactly what you have over here. So dEs d theta you can say is En. So now what we wanted was del of Es del S. So this I can write as del of Es del theta into d theta ds. Now if I say this is my reference point, this is the arc length S and this radius is R, you know that S is R times theta, or theta is S by R. So what is d theta ds? D theta ds will be 1 upon R, because theta is S upon R. So what you have here is, this is 1 upon R into En. So del of Es del S is 1 upon R En. Now if you come back and look at this expression over here, I can write this as del V del T plus V del V del S Es plus V squared by R into En. So this is your centripetal term, the centripetal acceleration. En is pointing towards the center of curvature. So you can recognize this as the centripetal acceleration. Now let us go back and look at Euler's equation. So you're going to have, okay, let me write once again this expression. Suppose I say A is the acceleration of the fluid, which is dV dt, material derivative. We'll write it as del V del T plus magnitude V del del S of the magnitude Es plus V squared by R En. Now you're going to have rho times acceleration is equal to rho times G minus grad of P. So we'll go back and look at the coordinate system. We have a orthogonal coordinate system. This angle is 90. Es tangent to the curve, En perpendicular to this, and you can take what you can call a binormal EB, which is say Es cross En, and you can write the grad of P using this coordinate system. So grad of P I can write as del P del S Es plus del P del N En plus del P del B EB. So you're going to have you can look at the S component and the N component and the B component of this Euler's equation, and you're going to have, if you want you can call this rho B also, if you want to be consistent with the notation which Professor Chakravarti was using. And we are dealing with steady flow for the timing. So this term is 0, let us say. So if you look at the streamwise momentum equation, you are going to have rho into V del S, that is the term coming from the left hand side here, equal to rho Vs minus del V del S. And the other, if you look at the N equation, you are going to have rho V squared by R is equal to rho Vn minus del P del N. And the other one, there is no B component here, 0 equal to, or let me call this B1, B2, B3, otherwise you will get confused, minus del P del V. So this is the streamwise direction, this is the normal direction, and this is another normal direction, which is a binormal. Now you see that if the streamline is curved, then you have a centripetal acceleration here, and the pressure gradient must balance that. So even if there is no flow perpendicular to the direction, you cannot apply the hydrostatic relation for that. So for example, if you go back to that case where we inserted a pitot tube in a circular pipe, this is a straight pipe, and we are measuring the velocity at this point. Now suppose I give you a tube like this, which is curved. So the fluid is flowing along this tube, and the cross section could be a circle. It's a curved pipe. Now here, if I insert a pitot tube and make a static pressure tap over here, if I say this is this height is rho m, this is my manometer, sorry, this is hm, this is my rho m. Okay. The relation which we used earlier, this relation, this cannot be used to find the velocity here, because now the streamlines are curved. So because of this centripetal acceleration or centrifugal force, the variation of pressure in the direction normal to it will not be linear anymore. So nobody asked me any question when I looked at this case, which is not a fluid at rest, and to find the pressure at this point, when I use this, I simply use the hydrostatic relation. So this hydrostatic relation can be used here because the streamlines are straight lines, which means the radius of curvature is infinity. So the variation of pressure in the normal direction is 0. If you go back to this relation over here, this is the variation of pressure in the normal direction. If r is infinity, because they are straight lines, then this term is 0, and you can neglect the change in pressure in this direction. All right. Now let us look at the principle of a venturimeter. So here you have, let us say you want to measure the flow rate. So let me write here, venturimeter. Let us say you have a pipe of certain cross section here. So the venturimeter has a converging and diverging section. So you will have a taper here, and you could have a possibly a constant area section called the throat, followed by a diverging thing. Now this will be gradually diverging. And this side, the diameter. So this could be a circular pipe. So what you are doing is, the diameter here and the diameter here will be the same. You are going to insert this tube, what you call the venturimeter here, by attaching it here between these 2 points. Now the fluid is flowing this way, let us say. You make a static pressure tap here and a static pressure tap here, and connect it to a U-tube manometer. Now if I ask you the question, if I put a manometer fluid inside here, where will the level be? Will it be higher here or here? What do you think? Left side, because here pressure will reduce. Okay. This is not correct. It will go up. So this is your HM, let us say. So you have a fluid of density rho flowing through the pipe, and you have a manometer fluid of density rho m. Okay. Now you take a streamline which is along the center line. And you can apply Bernoulli's equation between point 1 and point 2, and that will give you P1 plus half rho P1 squared equal to P2 plus half rho P2 squared. So if you look at the difference in density which you can measure, P1 minus P2 using this U2 manometer, that can be linked to half rho V2 squared minus P1 squared. Now let us say I want to find the volume flow rate through the tube. The standard symbol is Q. If I know the area at section 1 here, now we are going to assume that the velocity profile A here is uniform. So it is going to be A1 V1. And if you assume the velocity profile at 2 is also uniform, this will be A2 V2. So the geometry is known, so you know what is A1, you know what is A2. So if you know either V1 or V2, you can find what is Q. Now what you are going to measure here is the difference P1 minus P2 using this manometer. And right hand side has two unknowns here, but there is a relation between them. So you use the, in addition to this Bernoulli's equation, you use this continuity or conservation of global conservation of mass, whatever you call it, to link the two velocities. So from these two equations you can find what is the V1, what is V2, and hence what is Q. This is the principle. Now the question is how to find P1 minus P2. Now the fluid in this U2 manometer is at rest. So if you look at this continuous mass of fluid, if I take a point A here and a point B here, the pressure here and the pressure here is going to be the same. We cannot say the same about, say, if I take a point here, C here and D here, these two may not be the same because the fluid is different. Now here comes the assumption. We are going to assume that the streamlines here are parallel lines here. There is a curvature here, but here they are going to become like this. So in this normal direction here, the pressure variation is going to be hydrostatic because the streamlines are not curved. Now if I put a pressure tap here, static pressure tap, if you want the difference of pressure between this point and the wall, you cannot estimate it by the hydrostatic relation because there is a curvature of the streamline, whereas here there is not. Similarly here there is not. So you can say that you start with PA equal to PV, and PA you can write as P1 plus rho G. If I say this height is say H, then rho G H plus HM, the total height. And the right hand side is PB, which is P2. Now here there are two fluids, so you have to do it separately. Rho G H plus rho M G HM. Now as before, this term will cancel out, this rho G H, and you are getting P1 minus P2. If I move this term to the left hand side and I move this term to the right hand side, and note that GHM is common, so you have the difference of the densities rho A minus rho coming into G into HM. So this is what you want because that is what is on the left hand side of this equation. So you know what is rho, you know what is rho M. If you can measure in the lab this HM, the manometer deflection, and you know what is G, then you know what is P1 minus P2. So from that, if you want, I can write this as half rho Q squared by A2 squared minus Q squared by A1 squared. Then you have only converted both to one unknown, Q. Okay, A1, A2 are given. So this left hand side you have found, and right hand side Q is unknown, so you can easily find it. So let me write it down on the other side. You have P1 minus P2 is equal to rho m minus rho GHM is equal to half rho Q squared into 1 upon A2 squared minus 1 upon A1 squared. So this I can write as half rho Q squared A1 squared minus A2 squared by A1 squared A2. So Q squared turns out to be twice rho m minus rho GHM by rho into A1 squared A2 squared by A1 squared minus A2 squared. Now here A2 was A1 is greater than A2 according to this figure. So your A1 square minus A2 square will be a positive quantity. So here I can look at it this way. I can suppose I factor out A1 squared, then I have 1 minus A2 by A1 whole squared in the denominator, and here I have A1 squared A2 squared, and this remains as it is, rho m minus rho by rho G HM. So this A1 squared will cancel out. So from here your Q will be, if you take the square root, twice rho m minus rho upon rho GHM into A2 by under root 1 minus A2 by A1 whole square. Now this is assuming that you can apply Bernoulli's equation in the form which we have used. Now for viscous fluid, this will not give you the right result. So we can define what is called a coefficient of discharge. We will call it C with the substitute D, which is the actual flow rate by, you can call it, I will say just Q, the theoretical flow rate. Of course, this is assuming that Bernoulli's equation is valid, whatever expression we got. Now you can do a calibration experiment in the lab and measure CD for different flow rates, and this CD will be less than 1 because of viscous losses, and the losses are going to be characterized by a non-dimensional number which you are familiar with. It's the Reynolds number. So for a given geometry, A1 A2 ratio, your CD will be a function of RE. So this variation of CD with RE we can find by doing an experiment, and finally then the Q actual will be CD into what you had with the function of RE twice rho m minus rho by rho GHM A2 by under root of 1 minus A2 by A1 whole square. Okay. Now the geometry is known, so you know what is A2, you know what is the ratio A2 by A1, you will know rho m rho G, you know. So HM is what you will measure in the lab. Now the problem is that this is unknown. So this RE you can define as the average velocity into some length scale, could be the diameter, by kinematic viscosity. Now this V, average velocity, will be say Q or Q actual by some area. Okay. So if I take this to be the upstream value, then I will take it to be the A1, the velocity in the pipe. Now you see that this Q actual is on the left hand side of your equation and is also appearing on the right hand side of the equation. Okay. Now how do you solve an equation of that form? But there is only one unknown. You measured HM in the lab. Okay. So if somebody fits a curve from your calibration experiment, you know that. So what principle will you use to solve this? You will have to iterate. But luckily for you, if the Reynolds number is large and the flow is turbulent, then the CD will be independent of RE. That you can verify in the from your calibration experiment. Okay. So if you iterate also, the first guess you will take is the value at the high Reynolds number. So take the value when the Reynolds number is large, some constant value, and if the Reynolds number is large, then that is correct. So you don't have to iterate. But in principle, it can also be done iteratively. You have to first do a calibration experiment and fit a curve which tells you how CD varies with RE for a given geometry. That is for the vectorimeter which you are going to use. Okay, now let us talk about an orifice meter. So here what you have is would be a tube, and you have a orifice plate. I am not very good in drawing, so I am just giving you a sketch. A sharp plate with a hole in the center. So this is what you call your orifice, and this could be your flow direction. Now if it is a viscous fluid, you will see that when the fluid is flowing from left to right, it will come out as a jet here, and if you take the streamline which is passing here like this, you will see that these streamlines will converge. So there is a sort of contraction, and then again it will increase, and this way it will go and attach with the wall here. So this point is called the vena contractor, and if it's a viscous fluid, there may be a separation here on this side also. So there will be some eddies here due to flow separation. Now what we will do is, we will put a static pressure tap here. If you can estimate where the vena contractor will, of course this will depend on the flow rate or the Reynolds number, whatever it is, but suppose to develop the theory, we will put a static pressure tap here, and we will put a static pressure tap here, and connect it to a U2 manometer. Now you can proceed as before by taking a central streamline and applying Bernoulli's equation between, say, this point 1 and this point 2. So it is straightforward. I am running short of time, so I will not write down all the detailed algebra, just give you a brief discussion. You see here why we are applying it between this point and the Wiener contractor here is that if you look at a streamline pattern, the curvature of the streamline is going to be least at this section. If you look at the streamlines which are here also, they may not be exactly straight lines parallel to the axis, but almost straight. So in this perpendicular direction, you can use the hydrostatic relation. We have argued that if you have streamlines with strong curvature, then the pressure variation in the normal direction cannot be obtained from the hydrostatics, because there is that centripetal axillary term coming. And similarly here also, we are going to assume that the streamlines are like this. Now, if I put the manometer liquid here, you tell me again which side will be higher. Now, let us compare a venturi meter and an orifice meter. For the orifice meter, in both cases, ultimately what you are going to measure is this height, deflection HM. And in any experimental measurements, you are going to have an uncertainty which is determined by the least count of your scale. Okay. So there is an uncertainty in this measurement which is, say, delta H by HM. Now, if it's a simple apparatus, this delta HM may be 1 millimeter if you put a linear scale in the lab. So if you look at the relative error in this measurement, it will depend on the flow rate, because this HM depends on the flow rate. And the larger your HM, the less will be your relative error, and you have more confidence in your measurements. Okay. So you want always that this manometer deflection should be as large as possible for a given pressure drop. Okay. Now this pressure drop will also depend on what the density of the fluid. So if you have say water here flowing through this pipe, you can use a venturimeter. Now if you have air, if you replace the water by the air, then this deflection might reduce. If the manometer deflection reduces, then your relative error will go up. So there, if you use a orifice meter, your H might be larger because of the losses. So typically you would use an orifice meter if you are measuring flow rates of air at low Mach numbers, which you can still treat as incompressible flow with constant density. So in the afternoon session, we will have tutorials where we can continue further with this discussion.